Every time you turn on your mobile phone, it has no idea where it is. No cell, no signal, and no clue which frequency to listen to. Somewhere out in the 5G FR1 band from 14 MHz to around 3.98 GHz of spectrum, one specific channel is being broadcasted by the G node B, and your phone has to find it blindly. There is no GPS assist, no hint, just raw searching hundreds of thousands of channels wide. And it does so in a fraction of a second every single time you power on your mobile device. In this video, we will look at how a 5G phone finds a cell from nothing. Today, we are breaking down exactly how that works in 5G NR using band N71, the 600 MHz band, as our example. Here is our device, powered off, no connection to the network at all. The moment you hit power, the modem boots up and immediately starts hunting for a 5G cell to camp on. But here is the catch. It doesn't know the exact frequency yet. All it knows is which band to search, in this case, N71. Band N71 is a FDD band. The downlink, which is the direction from the mobile tower, the G node B, to the phone, spans 617 to 652 MHz. That's a 35 MHz slice of spectrum that the UE has to search. Every valid frequency in NR is identified by a number called as the NR ARFCN. That's the absolute radio frequency channel number. It is built on a global raster, which is a common 5 kHz grid used across every NR band in every range. For band N71 specifically, the actual channel raster, which is the spacing between real usable channel centers, is 100 kHz. That still works out to roughly 350 possible channel positions across this one band. Scanning every single one at a time would take far too long. So 3GPP defined a second coarser raster used only for synchronization signals, that's the PBCH block. This is called as the sync raster or GSCN. The full form of GSCN is Global Synchronization Channel Number. For band N71 at 15 kHz subcarrier spacing, the applicable GSCN range is 1547 to 1624 in steps of 1. This is defined in 3GPP spec. It is built from this formula. SS block frequency position equals N into 1200 kHz plus M into 50 kHz. And GSCN equals 3N plus M minus 3 by 2. For band N71, at 15 kHz subcarrier spacing, the applicable GSCN range is 1547 to 1624 in steps of 1. That's only 78 candidate frequencies to check instead of 350. This is the blind search. The UE steps through each GSCN candidate one at a time, correlating for the presence of a synchronization signal. Most of them come back empty. There is no cell there. Until it hits one, which is the GSCN 1600, which works out to 639.85 MHz. Thus, energy is detected, and this is where the network actually placed its SSB. Now it decodes the PBCH block, the SSB. Firstly, the primary synchronization signal is decoded. This gives the UE symbol timing plus one part of the cell identity. Next, the SSS, which is the secondary synchronization signal. And together with PSS, SSS forms the full physical cell ID. The remaining symbols carry the PBCH, which delivers the master information block. This includes the system frame number, the subcarrier spacing in use, and critically, the offset to point A. Now, point A is the center of subcarrier 0 of common resource block 0. Given point A, it is possible to find the offset to carrier and the channel bandwidth. Thus, offset is the key. It tells the UE exactly how far the SSB sits from point A. Point A is the frequency reference for the carrier's actual resource block grid. Once the UE calculates point A, it knows the true center frequency of the deployed carrier. In this example, 635 MHz, and then it can convert that back to an ARFCN value. Thus, the channel roster is resolved. The UE now knows precisely where the carrier lives. So to recap, the ARFCN and channel roster are the fine global numbering system for every possible frequency. The GSCN and sync roster are a much sparser subset. They are just enough candidates for the UE to blind search quickly. And once it decodes the MIB, the UE resolves the real channel roster, the exact frequency the network is actually using. 3 rosters, 1 cell search.